Hi all. I want to just give a quick summary of the exam review session. The recording did not work out, unfortunately, for technical problems, but also this summary will be a bit quicker. It will focus on the main ideas and hopefully give you some ideas for some last-minute review. So one thing about this practice exam is that you may have found it harder than many of our homework problems. You may have found it quite challenging. Some good news is that I intended it to be hard, and the actual exam will be considerably easier. And the main way that you can practice for the exam is to review the lecture notes, review the homework, and review the main concepts of the class. In the beginning of the review session, together with the students who were there, we collected some of the important concepts in this diagram. I will put this diagram also on Moodle, but what you can see here is that we have concepts from the beginning of the class that are very important. One big theme that we spent about a week on, which was definitions of topologies. Related notions, so closure, interior, boundary, accumulation points, continuous functions, and comparing topologies, coarser and finer topologies. This was one module that we spent about 1 to 2 weeks on. Then we talked about separability and denseness. These were related to each other. Compactness, we spent quite a bit of time on, and we did a little bit of bare category, a few examples. And after that, we moved on to a new theme that we spent the last 2 to 3 weeks on, which was quite challenging, but which was about defining topologies. We did this by talking about bases and subbases, also neighborhood bases, and then introduced concepts like N1 and N2. Then we talked about product spaces and inducing topologies, and quotient spaces and co-induced topologies. And if you want to organize these somehow, here we have functions from x to y, and we want to define a topology on x. And the most important example is that we have a product space and a projection on its factors. And in the quotient case, we're going exactly the opposite way. We want a topology on the target. So try to touch in your view on all of these concepts. Remember the definitions, remember some of the important results, and review some of the homework problems related to them. Now, I will go over the problems of the exam, saying something about them all. There are detailed model solutions of these problems on Moodle, so I will not spend detailed time going over them. I'll try to focus on what you should do on the exam when you're thinking about them. So I will upload these solutions. First, there are these notes that were from the lecture that you might find useful. If you want, you can look at them. But instead, I will structure this quicker review by looking at these model solutions. And I will highlight some things that I think are important. So when you're on the exam and you see a problem, the first thing you should do is to highlight the important words. Highlight them for yourself. So in this problem, the first problem, the important word is accumulation point. And what you should do is recall the definition of accumulation point. So X is an accumulation point of E if for all neighborhoods of X, neighborhoods U of X, we have U intersected with E, take away the single point is not empty. Okay. In your exam review, remember all the definitions of the concepts because you will need to use them in the exam. What might be also useful is remembering a few different versions of the definitions because different problems may require a slightly different version of the definition. And one good example in this here is the closure, because this problem actually becomes a lot easier if you define closure as the union, or if you use the result that the closure is the union of the interior of E with its boundary. This was something that we had in the homework. But what I will actually use here is only the fact that E bar is the smallest closed set containing E. Yeah, and this can be used as follows. So if X is an accumulation point of E, then when X is not in the closure, you look at the complement. And the crucial part here in this proof is that the complement of the closure is open. And that's because the closure is the smallest closed set. But the complement is disjoint from E, and this contradicts X being an accumulation point. The other direction, part B of this question, is significantly harder, and there was a typo in the earlier version, and you need to assume Hausdorff to prove this result. This proof is quite a bit harder, so I will not emphasize it, but what will help you a lot is to have a picture. So I will draw a picture just for this proof. So we have our set E, say it's this disk without its boundary. Then we have, this is our set E. Then we have the accumulation points of E. It's something along this boundary here. This is A. And then we have a point here that is an accumulation point of A, something like this. And what's happening here is that accumulation point means that every neighborhood intersects a set. So if the red point here is an accumulation point of this green set, then we find some point in this green set, which in this proof is called Y. And then where the trickiness lies is that we can find, since Y is now in A, Y is an accumulation point of the set E, since A consists of the accumulation points of E, and this purple set here is a neighborhood of Y. So we can find another point, let's call it Z, that lies in E intersected with U. The proof is not quite that simple because we have to guarantee that this Z is not equal to X, and this is where we have to use the Hausdorff in this crucial step. So this proof is not easy, but what I want you to get out of this is being able to draw this picture. And in the exam, I can assure you the problems will be more straightforward, and such a picture will help you a lot. Let's move on. You're sitting on the exam. We look at problem 2. Now, what you should highlight here: compact, Hausdorff space, compact, and I would like you to also notice that you have the intersection here. And if you've done your reviewing well, you'll remember that in the homework we did something almost similar. We talked about unions of compact sets. If you remember the very dense lectures well, then you might remember that we talked exactly about this question in lecture. But the concept here that is often very useful in compact sets, so you have two ways with compact sets. There's the open cover definition, That's very often useful. You should try that on the exam. In this problem, it will not help you, unfortunately. But what will help you is the following two facts. That if K is compact and C is a subset of K and C is closed, so a closed subset of a compact space is compact. So that helps you in one direction, because what it tells you is that it's enough to prove closedness to get compactness. And this is almost an if and only if. If you have X is compact in Hausdorff, and C is a subset of X which is closed, then C is compact. So there are these two facts. So you can think of them as going the other direction. So here we're going from closedness to compactness, and in the other case, one direction here is wrong. From if C is a compact subset, then it is closed. Yeah. A compact subset of a compact Hausdorff space is closed. And how this is useful is that these go in the opposite directions. Or in the first one, we go from closedness to compactness, and in the second one, we go from compactness to closedness. And indeed, when you look at this proof, we use this in two directions. First, we conclude that K1 and K2 are closed because they are subsets of a compact and Hausdorff space. And then we conclude that the intersection is closed because the intersection of closed sets is always closed. And finally, we conclude that this closed set is compact because it's a closed set of the compact space. Again, there's a thing that this counterexample is difficult to think. And one thought for the counterexample is that if you want an example of a non-Hausdorff space, or actually, yeah, in general, the examples that you should think about, we have covered, especially during the first week, we had a bunch of examples. There's the trivial, there's the discrete, there's the special point topology that was defined at one lecture, and these are, and then there's the cofinite and the co-countable topologies. These are some of the most important ones. Unfortunately, for this problem, we need a more complicated topology, and it's a version or a variant of this special point topology. The only intention here I can think is that you think of standard constructions of topologies, and if they don't work exactly, then you try to modify them. And again, I want to assure you that on the exam, standard example should be enough. That this was quite hard because it required this odd topology that we haven't much talked about. Now, next problem was about this co-compact topology. We had a portfolio problem about this related to this. So, and we had this is also a bit similar to the cofinite topology. So what can help you a lot on the exam is to try to bring analogies, try to remember what you did in the related problems, even if they were not exactly the same. And in this problem, that is best exhibited in this compactness proof, because this is exactly like in the cofinite topology. If you go through your problems, you have a covering of your space. The complement of one of the sets is compact, and that compact set has a finite subcover. And then you combine the covers together. If you want to understand this well, then compare it to that proof for the cofinite topology that we had on 1 week's homework. From these problems, this part C was a lot more difficult, and it's not so interesting, so I will just leave it at that. If I will ask about N1 and N2, the sets will be quite a bit easier, but maybe what you should take out of this is that especially using these balls, so if X is separable and metric, we had a result that X is N2. And here, how we did this was that we took S is the countable dense set, and then we took the balls B, S, 1 over N, where S is an S and N is a natural number. This was our countable basis for the space. It's a very instructive problem to think about why that is a countable basis, but we did that also in lecture. Good. Moving on. Problem 4. Big thing here is basis for a topology tau y. And now in the lectures, we spent a lot about effort defining a basis. But what is important is not the definition of basis, it is how a basis for a topology tau y. And there are 2 definitions. That the first one here is that we say that B is a basis for tau y if for every open set O, every point inside it, we can find a basis element B that's inside here. The other one is more complicated. You can do most proofs using it. Tau y, the smallest topology containing B. And this was also called inducing or generating. Those are the same things, or result in the same thing. So you can do a proof with both of them. In the lecture notes, I've done one of the proofs, and here I do another proof. I feel that this proof might be a bit easier just from this purple definition of a basis, that I think is the more important definition of a basis. And I think what will help is the main thing is that you keep track of where the points lie. So if you want to show that the pre-image is open, then you look at the image. That's the one important thing. And one thing that we used a lot in the beginning of the class that can be very useful is that a set O is open is the same thing as saying that for every X in O, there exists a neighborhood B such that X is inside B is an O. And I write it like this with B because now I think of B as a basis element. And this is exactly what the proof shows. For every X in the pre-image, we find a neighborhood that's now the pre-image of B that is contained. Good. So this often will be a useful tool in proving openness. It's equivalent to saying that the interior of O is equal to O. And this problem had a second part, which was about basis for the product topology. And if you see this on the exam, do it. You might not like the product topology, but if you have a basis for the product topology, just write it out because it's very simple to write out. The basis for the product topology consists of all these rectangular set with a base at U and V. U times V inside this product set of X times Y. For 2 factors, this is very simple. For finitely many factors, it's simple. Where things get a little bit confusing is when you have countably or uncountably many factors. But for finitely many factors, this is simple. And but one thing about the product topology that you might want to review is that Pn converges to P in the product topology if and only if it converges pointwise. or component-wise. And if you don't know what these mean, or you struggle with this, I suggest strongly to review that, because that's one of the important concepts of product topologies. Good. Then problem 5. I will not say much about here, except that remind yourself about induced topologies, basis, subbasis for an induced topology. Those can be very helpful. Then what can help you is a lot this picture. So the induced topology is that we have these topologies on tau a, xa, tau a, and we want to get a topology on a space Z that maps into them. So we go backwards of the function. And in this problem, so how to get a topology on Z, the simplest way to state it is here. It's the course's topology such that FA is continuous for all A. That doesn't tell you very much about the topology. The other one is you take a subbasis consisting of the pre-images of open sets. This is a subbasis for the tau induced. In the lectures, we talked a lot more about this. There was one result that we talked about, but we didn't maybe focus enough. But there is this special diagram here that if you have a mapping from Y to Z, then we get, and this is called here G, and if we look at the composition of G and FA, then this arrow here is continuous if and only if this arrow G is continuous. And one direction is easy, because if G is continuous, then the diagonal arrow is a composition of G and FA. And the induced topology is defined so that FA are continuous. That's the important feature of that topology. So G composed with FA is continuous because FA and G are continuous. So this is the first direction of this proof. The other direction is what is harder. So in lectures, we did one proof using a subbasis. Here I write a different proof using the idea that this is the course's topology that such that FA are continuous. And this proof is maybe not the easiest to follow. It uses the idea of this co-induced topology and argues that the co-induced topology actually contains the induced topology. Now, if you want to understand this, you'll think, how do you show that tau induced is contained in tau G? It's all written here. And the big thing is this diagram. And you should look at these diagrams a little bit. They are written in the lecture notes, and they're talked about there. So there's one for product spaces, induced topologies, and there's another diagram for co-induced topologies. And I'll just show you what the diagram looks like. There we have the arrows go exactly the opposite. So we have functions x. We have functions going down to Z, and then we have a mapping from Z to Y, G, and the diagonal mapping FA, G composed with FA is continuous if and only if G is continuous. But the definition of the co-induced topology is a little different, and it's a little bit simpler. So, but to review these concepts, induced and co-induced. Now, problem 6 is very simple. This is a type of problem that you definitely want to do on the exam. If you see that the problem talks about interiors and closures, it's concepts that we talked about very early in the class that we've practiced many times in this course. So really, you have the tools to solve these. These should be easy problems. Don't shy away from them, do them. And here, if X is an interior, you can read these. I won't repeat them. These just follow from the definitions. Just exhibit here. If X is an interior point of BA, then there is some neighborhood that is contained in it, and that contains X. For that, closure is the smallest closed set containing BF. There should be closed here. And since F is another such set, then so it's really these basic properties that we've used to practice. And yeah, in part B is a little bit more complicated because it's harder to use that fact that you're the smallest closed set. But remember that maybe the notation, you can switch like here. And the thing, if you want to show that the closure of BA is contained in some subset F, this is the same thing as saying that F is closed, or it's not the same, it's implied by F is closed, and F contains the intersection of the sets. Because the closure is the smallest such set, then it's automatically. So this means that you can check just two things. And in this case, they're quite simple, like the intersection of closed sets is closed. And we're already at the end with this very quick summary. So this is an abstract problem. It has a fairly short proof, but if this was on the exam, what should you do? Basis for it. So we need a basis. We need compact, and then we have to look at this condition here. And the thing here, what I've written, and this I've often, you'll write such things, we've done similar things in the homework, is that when you have a basis, it's generally enough to check the properties for that basis. In general, you can have an arbitrary open cover, but here we're looking at open covers that consist of basis elements. But these properties are often equivalent if you write them correctly. One of the directions is always easy. Here, what does compact mean? Every open cover has a finite subcover. So in particular, if the open cover consists of basis elements, like in this blue shaded sentence, then that has a finite subcover. So one of these directions is easy, and it's done first. The other direction is a bit harder, but I'll draw one picture that should help you. You have your space X. It's covered by these blobs U, and there's finitely many of them that you are enough. But these blobs U can look very weird, and what we're saying is that it's enough to cover with basis elements. And what can we do with basis elements? Well, for every point in X, we can find a basis element that's contained inside one of our pieces. The point is contained in one, and the block is contained in the other. So every point is belonging to such thing. And once we have for every point, then we can construct a cover of it. But then you can use this. You cover the space first by these blocks that are entirely contained in one of these spaces. And each of them is contained in one of them, and you only need finitely many. So once you take the finitely many pieces and replace them with the set that contains them, then you're good. Just be careful with the notation. Don't confuse yourself. Try to have a clear picture. Try to have a clear picture of what you're trying to do. These will help. Again, this is a bit of a harder problem, but on the exam, when the problems will be simpler, remember the definitions, draw a clear picture, try to understand at first what is being shown, and try to compare it to what we've been doing. Good luck on Wednesday. I hope it goes well.